To all audience today's webinar. So it is my pleasure to introduce Juan Carlos Algaba Marcos. He did his PhD at University College Cork, Ireland, and then he went to several postdocs. So the last postdoc he did from Seoul National University, South Korea, and recently he is a senior lecturer at University of Malaya. His research interest is related to active galactic nuclei and very long waistline interferometer. And today he will be talking about first results from the Event Horizon Telescope. Please, Carlos.
All right. Thank you for the presentation. You probably have already heard the news about what the first results from the Event Horizon Telescope are. Basically, the image of the supermassive black hole in M87. Can you hear me? Okay, is that fine?
Yeah, the voice is clear.
Okay, good. At the beginning, I will just show you a little of the contents I want to discuss. First, maybe having a small review about black holes and what we knew before, what we know so far, and what is the idea, what else we want to know from the black holes. Then, of course, it is very tricky to observe black holes. Number one, because they are black. But number two, also because they appear very small in the sky. So that means that we need a very high resolution in order to be able to observe them. So I will be discussing about how we can obtain the needed resolution and what kind of techniques we use for that. And in this context, I will introduce just a bit of the Event Horizon Telescope, what are the capabilities of the telescope, and what are the engineerings and everything that has been involved in the technical aspects of the Event Horizon Telescope, EHT for short. And finally, I will show the first picture of the black hole and discuss a bit of the science that we can already do with this image. Later, I will also discuss what else we can do, something like future prospects or further ideas, and finish with some conclusions, or in short, let's say the 4 or 5 key points that will be the fundamental ones to keep in mind after the talk. So, basic idea is that black holes, even though they have been in the culture, or let's say in the popular imagination for a certain time, they are not really anything new or something that is only delegated to science fiction. Already Mitchell in 1783 was considering what would be the escape velocity of different objects and consider what kind of object we would have to consider if we would have to estimate escape velocity, which would be equal to the speed of light. And he considered that if we imagine something with the same density of the sound, roughly speaking, we would need an object with 500 solar masses in order to achieve this escape velocity. At that time, however, it was considered such a mathematical exercise, let's say, or an exercise that one would put to students to calculate different escape velocities. But it was not really considered that light would be affected by this kind of gravitational effects. It was not until Einstein's equations, and in particular the solution from Schwarzschild, that it was found that there will be indeed some sort of solutions where we would have some sort of object that would be able to attract the light and attract it in such a way that light wouldn't be able to escape because of its gravitation. And that object will be such that after a certain radius, what we call the Schwarzschild radius, the light wouldn't be able to escape from it. Again, this was just considered a mathematical solution for Einstein's equations, and people didn't really consider that these objects could actually exist in reality, because there was not a real feeling of a physical process that could actually create such objects. We had to wait until Oppenheimer in 1939 when he came up with a method or a way where stars could collapse, and then the gravity wall could overcome Pauli's principle, and by this phenomena, actually some actual objects in the nature will be able to create these kind of objects that would actually attract light so much. But it was not until 1967 when people was still talking about this idea and still having the feeling that something in the nature would prevent these objects to form. That there was this discussion where some people was in some sense talking about these terms and using the term black hole to make fun of such idea. Eventually, as similar things are happening with the Big Bang, for example, the term that was initially chose became the usual term to refer to these objects. And today we refer to them as black holes, as in the scientific literature. So basically, we know what is the background of the black holes. The question that we have now is, we know that this is not a mathematical solution. We know that there is actually a physical process that can create these objects in nature. The question now is, do they actually exist in nature? Or that means, in some sense, if Einstein's theory is ultimately right, because we had checked the theory in many ways, for example, with the solar eclipse, or for example, with the gravitational waves. But in some sense, we need to check the strong gravity regime and very compact objects, or let's say in some sense, these regions where Einstein's theory predicts that space-time will basically have a singularity. We had to really check these kind of objects to figure out that even in the strong cases, even in the most extreme conditions, Einstein's theory is still right. So what we had to ask ourselves is, what is the observational evidence? We want to check if black holes actually exist. We want to check what is the evidence we have. And this is not as simple as just checking a telescope and looking at the sky, at a blank region of the sky, and just looking there saying there is a black hole. It's not as simple as that. We really have to do a lot more effort. So what do we need to do? Well, there are different methods. One of them will be looking at stellar orbits. For example, Andrea Gles in the UCLA Galactic Center group found what would be the orbits of different stars that are orbiting around a central object in the center of our Milky Way. And she found that many of those stars, as you can see in the figure, will be orbiting around a central object that we cannot really see. And by calculating their periods, they were able to check that this object in the center, which must be very compact, must be, of course, much smaller than the region of the orbits, nonetheless has a very huge massive mass of the order of 3 or 4 10 to the 6 solar masses. And the only objects that we can think about that will be so small and at the same time such massive would be black holes, basically. If we can think about anything else, it would be so much that would be even more exotic than black holes themselves. So in some sense, this is one of the evidences we have for black holes. Another idea would be to study the water mega masers that will be in the center of some galaxies, for example, NGC 4258. We can also check the speeds of the mega masers and make some Keplerian or orbital fit to these masers by just looking at the speeds and velocities. And we can also have an estimate of the mass that is in the center of these objects. And again, what we can observe is that in the center, in a very compact region, there should be a mass that is of the order of 10 to the 7 solar masses. Nonetheless, to say, this is also suggesting that whatever is in there in such a compact region with such a big mass is probably a black hole. There are other ideas, for example, checking accretion disk, and in particular the iron K alpha line. Whereas if we suppose that there is some strong gravity affecting there, say gravity that would be coming from a supermassive black hole, then of course we should consider how the special relativity, the general relativity is going to affect the emission lines. And when we consider these things, of course, we will be able to obtain some, let's say, theoretical line profile for the iron K alpha. And this theoretical profile has been actually been observed. And the fit is pretty much very nice. And we can also discuss that the object that is causing this kind of phenomena for the iron alpha lines is going to be, again, a black hole. For me, personally, one of the most interesting proofs, or let's say indication, that there is a supermassive black hole in the center of galaxies would be the extragalactic jets. In this picture here, I don't know if you can see the mouse now. The center of this galaxy, that will be Hercules A, is expelling two extragalactic jets. These jets are highly collimated, so of course they don't become very wide until they have reached regions that are very much farther away from the galaxy itself, and they are traveling to speeds that are close to the speed of light. When we do the calculations, the only object that we can think that can power such powerful jets are, again, supermassive black holes as the central engine in the center of these galaxies that we call active galactic nucleus. So, yes, we have different methods and different ideas and different objects where we consider that the ultimate object, that the central engine, or whatever is causing what we see, must be a black hole. But the problem is that all of these ideas, all of these examples that I have provided, are only indirect evidence. It could be a supermassive black hole, as everything seems to suggest, but we may also be totally wrong with these assumptions. It could be something else. So in that sense, what we have to do is actually obtain direct evidence of what is a supermassive black hole. The idea is the black hole itself is black. What we want to do is imaging the black hole shadow, which is basically the shadow that the black hole is casting over the material that is surrounding it. Normally, this material will be some gas or some accretion material or some ions that is basically falling around the black hole. And as you can see in the picture, when this happens, the light from the surroundings will be deflected because of the gravity of the black hole, and we will be able to see this black region in the center of the bright objects. Normally, the shadow of the black hole would be of the order of 5 times larger than the Schwarzschild radius. It, of course, depends on several parameters. For example, what is the black hole spin, how fast it rotates, what would be the inclination angle, and etc., etc. But roughly speaking, for the matter, or just to simplify things at this level, we would say that the black hole shadow should be about 5 times the size of the event horizon itself. So we had the backgrounds, or let's say the idea on how we can actually observe the black hole, basically by looking at the shadow over the bright objects around them. The second question that we have to consider is how big the black holes will be in the sky. And for this, I will discuss about the resolution. You know that if we look at the sky from horizon to horizon, this is going to be about 180 degrees. So basically, the moon is about half a degree, or let's say 30 minutes of a degree, or arc minutes. Every arc minute, again, will be form of 60 arc seconds. So, for example, Jupiter, as seen from Earth, will be around 1 arc second. And then we can discuss a smaller and smaller region of the sky, which means better and better resolutions. Just to make an idea, 1 milliarc second would be the size of a dime in the field tower, as seen from New York. And if we go even to smaller details, 1 micro arc second would be basically the size of a dot in a notebook that, let's say, Neil Armstrong, for example, forgot on the moon, as we can see from Earth. So we have an idea of what is an arc minute, an arc second, milliarc second, micro arc second. Now the question is, what is the regime we will be talking about when we want to observe a black hole? How big, or in some sense, how small would a black hole look like in the sky? So we are going to see the black holes that we have around us. Most of them will be stellar mass black holes around in our own galaxy, except the supermassive black hole that we have in the galactic center, which of course is still nearby, and it looks quite much larger than stellar mass black holes. On the other hand, we can also look at supermassive black holes that will be much farther away, and then of course they will be much, much bigger but they wouldn't really look that much larger as the apparent size of the sky, except maybe the largest ones around, which are still in nearby galaxies. For example, the black hole in M31 or M87, or the extremely large black hole in HGC 1277. So if we put this in context, and let's check which would be the largest apparent size black holes as we look in the sky, the three best candidates for this would be Sagittarius A star, which would be the black hole in the center of our own galaxy, with a mass of about 10 to the 6 solar masses, 8 kiloparsecs away, which means that the Schwarzschild radius is about 11 microseconds as seen from Earth. The shadow size, of course, about 5 times larger, would be around 50 microseconds. The next best candidate would be M87, which is about 1,000 times larger, but is also about 1,000 times away. So this means that, roughly speaking, the apparent size in the sky would be very similar to that of Sagittarius A star, about 8 microseconds. And when we go to the third candidate, Centaurus A, even though it's kind of the third best option, is already about larger than 1 order of magnitude smaller in the sky. So the idea is we can stick probably to the two best candidates, Sagittarius A star and M87, which about 50 microseconds for the shadow size. Now the question is, we know the black holes are going to be very tiny, of the order of microseconds. How can we do? Let's pick up what are the best telescopes that we have in the world right now. For example, the Grand Telescope of the Canarias, which is a 10-meter dish. And the resolution we can achieve with this telescope is about a quarter of an arcsecond. Even when we consider the China-Magellan telescope, which is currently under construction, with an expected size of 24 meters, we can get something like 0.01 arcseconds. This is still discussing the size of arcseconds, whereas the size of the black holes, the apparent size for the best candidates for the black holes will be on the order of micro arcseconds. So we are still very far away to actually be able to reach these resolutions. The question is, what can we do here? Well, the obvious solutions would be the resolution is proportional to the size of the telescope. The larger the telescope is, the better the resolution becomes. Maybe, can we make bigger telescopes? No reality. As we can see, our best efforts are still way beyond the resolutions we need to achieve. If we want to get 1,000 times better resolution, we should be able to make 1,000 times larger telescopes than the ones that we have now. And of course, this is technically not feasible for our techniques currently, or quite possibly for the next maybe decades or centuries. I don't know about the centuries, but definitely it's going to be a big trouble for the next decades. So this is something that we cannot really achieve. The solution, however, comes via interferometry. Interferometry is a technique that is used to actually simulate a large telescope by actually using simultaneously a set of different telescopes at different distances, and we can actually get a virtual telescope which will be having a large aperture. Basically, in this sense, when we discuss what will be the resolution, it wouldn't be proportional to the size of the telescope. Using interferometry, resolution will be proportional to the distance between the telescopes. So that's to say, what we have to do is get a set of telescopes that are very far away. Then we synthesize or create or simulate this virtual single telescope, and the aperture we have will be of the order of the distance between the individual elements of this virtual telescope. Question is, how is interferometry working? If you are familiar with the double slit experiment, this would be a very easy example. We have a light source, or you can use a radio source and consider waves, or just typical waves from the water. And if we have a metal sheet in between with two small slits, you consider that each of the slits, or each of the holes, by the Hughes principle, is going to be creating another wave. And then, because we have the two slits, we will have two waves coming from them, and the two of them will interfere. And if we put a screen at a certain distance, it will be very easy to see the interference pattern. And this is a very simple experiment to do. We can do it with some water waves, or we can do with sound, or we can also do with collimated light, for example, coming from a laser. In the case of the telescopes, the situation is very much the same, only that for the light, the source of the light, we will have our own radio source. In this case, it's going to be the black hole. Instead of the different slits or the holes in the metal layer, we are going to have our radio telescopes, or the elements of this virtual big telescope that we're going to create. And these radio interferometers, these elements, are going to be collecting what is the shape of the wave at that location. What we are going to do is we are going to send these signals, or what the telescopes are obtaining, to a giant computer, supercomputer, that we call correlator. This correlator is going to be correlating the signal from the telescope and creating the fringes that we will be able to see from the experiment. The basic idea is because of the experiment, once we move the slits a bit, or once we change the wave a little, the fringes are going to be pretty much affected by this. Effectively, what we're doing with this is creating an object that will have much, much better resolution than each of the individual objects, because the fringes are going to be changing a lot. So what we are going to do is get the signal, get the wave from each of the telescopes, correlate to get the fringes, and once we got the fringes, by a series of mathematical tools in specific, a lot of Fourier transforms, we are going to try to recover what will be the original image that will be causing this kind of interference pattern. This is basically how we can synthesize these big telescopes. So we have interferometers already working on Earth. For example, we have the Very Large Telescope that is working on optical bands. Of course, because in optical bands it's very hard to obtain the different signals, the different waves at the same time. We cannot use very large distance between the telescopes. The baseline, basically the distance of the telescopes, will be of the order of just a few meters, or about 100 of meters. But even with this, the angular resolution that we can obtain is not about arc seconds anymore. It's already of the order of milli-arc seconds, which is a very huge improvement compared with single telescopes. On the other hand, we can also do the same experiment with radio wavelengths. That would be, for example, the case of very long baseline interferometry, in which case, because we're talking about radio waves, we can put telescopes much farther away, not hundreds of meters away, but thousands of kilometers away. And despite radio bands will be much lower frequencies compared with optical, but the distances will be much larger, the angular resolution we can obtain will be much, much better, of the order of a fraction of a milli-arc second, which is basically much more extraordinary, and would be basically the limitations of, or basically what we can achieve nowadays. So we can get from using normal telescopes or single instruments arc second resolutions to get milli-arc second resolution, or even smaller scales using this interferometric technique. What is our standing point today? Well, this will be M87. The Galaxy M87 will have a powerful jet, as the one I was showing before for Hercules A. And if we try to zoom in the center, where we assume the central engine is going to be this black hole, we can see the lower right image. Let me just point this in the, with a pointer. This jet will coming out from the center of the galaxy, and this will be
Hello?
about. Yes. Hello. Yes.
John, I have a question. So,
Yes.
how do you prove the sky location where the object is present?
Sorry, how we can check the location?
Yeah, a location of the object.
Okay, so that's pretty much straightforward. What we do is basically we point to that position in the sky with each telescope at the same time. Of course, this is not going to be enough, because the resolution is going to be much bigger than the resulting. But as I mentioned, when we are doing the fringes, same thing as the experiment, if we change the position of the source a little, the fringes are going to be changing a lot. So we can actually get the correlator to have a model and say we want to get the fringes for that particular location of the sky. And this is how we will be pointing to that region and pointing to this particular object.
So this fringes is gravitational waves or just light?
This is radio waves. This is very different from gravitational waves.
Okay. So so this radio wave is the light near about the speed of light, right?
Mm-hmm.
Okay.
Yeah. It's basically also electromagnetic waves.
Okay. Okay. Thank you.
So it's very different from gravitational waves. Like maybe we can discuss. So is this okay? Okay. So now with the lower left image, this will be of the order of about 1,000 Schwarzschild radius, and this will be already using this very long baseline interferometry technique, using hundreds of thousands of kilometers. What we can do now is try to push this to the actual limits or current limits, trying to get the longest distance we can do and kind of the highest frequency we can do, because frequency also affects the resolution. And on the lower left side, this is the best we can do for M87, or at least the best we could do before the past April. And still, we are about 100 Schwarzschild radius. That would be the resolution that we can get. So this means that still, to be able to get the black hole shadow image, we should get to get something like 100 times better than this. So we still have to improve a factor of 100. So now the question is, how do we do this? And here is where the Event Horizon Telescope, the EHT, comes in the game. Basically, what we are doing here is not only creating a network of telescopes that is as large as a continent, like the United States, from, let's say, Hawaii to the other side of the continent. In this array, we are doing a virtual telescope, or we are setting an array of telescopes that are spread around the whole planet. So in this sense, we have two telescopes in Chile, another in Mexico, another in Spain, Arizona, Hawaii. Even we have a telescope in Antarctica, in the South Pole Telescope. So we have an array that is as big as Earth, which is much better than what we had before. Second aspect, we increase the wavelength. This is also getting a better resolution. Normally, other facilities will be observing at 43 gigahertz, 86 gigahertz. The Event Horizon Telescope is observing at 230 gigahertz, or in terms of the wavelength, 1.3 millimeters, which is basically the maximum we can observe right now. This is the maximum that our instruments are able to achieve with the current technology. With this, we will have baselines or distances between the telescopes that range from 100 meters, in the case, for example, between SMA HACMT in Hawaii, to 10,000 kilometers, the case, for example, with between Pico Veleta in Spain and the South Pole Telescope. With this kind of setup, when we calculate the resolution, which will be basically the wavelength divided by the diameter of the telescope, or the diameter of this array, we expect to obtain of the order of 25 micro arc seconds resolution. And now this is really reaching micro arc seconds. This is really going towards the resolution that we want to obtain in order to observe the black holes. So now we have the setup of the experiment. We have to go for the Event Horizon Telescope itself. This, of course, is full of technical challenges. Challenge number one, we had to set up the network, which means we had to convince the different facilities that we want to do the experiment. And we have to include everything that the facilities need to be able to form part of this array. Because in general, if the telescope is observing by itself, we have to implement all the technology necessary to make the network of it. And this, of course, takes time, takes some technology, takes some development with that we have to take into account. Second part, we want to observe with all these telescopes at exactly the same time. Because, right?
Yes? Juan, sorry for disturbing. So this telescope, this telescope is useful for also LIGO calculations? Because you are talking about in this telescope you are detecting radio waves as well as for the electromagnetic data, right? And in the gravitational wave, sorry, they are detecting only gravitational wave, not in the electromagnetic data or
Oh, no, no, no.
radio, all these things.
I'm not talking about anything of gravitational waves. All the detections that I'm talking about is radio waves, electromagnetic spectrum. So this is not related with gravitational waves.
Okay. Okay. Thank you.
So
Okay.
what we're detecting is the radio part of the spectrum, 230 gigahertz of the spectrum, and what we're doing or trying to do is making them interfere so we can observe the fringes coming from the different telescopes.
Okay. Okay.
Sir,
Thank you.
Right?
excuse me, sir.
Mm-hmm.
Why this telescope is called as Event Horizon Telescope?
So basically, when the telescope was created, the idea was that this telescope will be powerful enough to actually reach to the event horizon of the black hole. So it's a bit as like calling this is a telescope that we expect to be able to use to see event horizons
Of the black hole.
of the black hole, right?
Okay. And what are these units? Micro, AS, MPC. The distance generally we measure in light years. So what are these units?
Um,
Distance in MPC.
you mean, for example, in this slide, when I said the resolution is 25 micro AS,
Yes, yes.
okay, this is
So
micro arc seconds. So this is, if you consider the angular sizes in the sky, you can, as I was mentioning before, the moon will be about half of a degree in the sky. You are considering
okay,
angular distances. So a degree will be having 3,600 seconds of a degree.
okay,
So I will be discussing about seconds of the degree, million seconds, or micro arc seconds of the degree in the sky. So this would be angular distances or how big in the angular scale an object looks in the sky.
okay,
Is
okay.
is this
Yes, yes, it is clear now.
okay?
And what is this unit MPC? In your earlier slide, you the distance was in MPC.
And that would be megaparsecs. So basically, one parsec would be about 3.6 light years, if I'm not mistaken. So that would be of the order of megaparsecs, or three times millions of light years away.
Oh, okay. Okay, sir. Thank you.
Okay. Then the basic idea now is all the telescopes have to be looking at the same source at the same time. If we want to do all these fringes, of course, if we detect the signal one fraction of a second later, the light has traveled already a lot of space in that fraction of a second, and we don't want to do that. We want to get the same signal at the same time at all the telescopes. So that means that we have to be very precise at the timing between the telescopes. For that, we need to use atomic clocks. And what we are going to do is getting a signal from the GPS for the time, and then we'll be adjusting what is the actual time very precisely with atomic clocks. For this case, we will be using hydrogen measures, and they are so reliable at this stage that if we have to wait until these clocks drift for 1 second, we should wait of about the order of the age of the universe right now. So they are pretty good, pretty accurate, but in some sense, this is actually the reliability we need from them. If we get off by a higher amount of that, they may not be that good. Things may not be that good. So we need this kind of technology to be able to make sure that at this frequency, we are able to synchronize all the telescopes. Another challenge will be how much data we are receiving. How much data is also proportional in some sense to what is the sensitivity that we can achieve, or how many dim areas we can actually observe from the black hole. So of course, the more sensitive we are to the radiation, the more information we can get. To do that, we have to record a lot of data. Now in this experiment, we were recording at 32 gigabps, if I remember properly, which basically means 32 gigabytes of data every second. So for that, of course, we were recording for one day. We had 4 experiments in 3 different days. We were typically recording about 12 or 24 hours, and we were recording in over 8 different telescopes. So you can multiply 32 gigabytes per second, multiply by 3,600 seconds in 1 hour, multiply by 24 hours, multiply by 8 telescopes. So you can already imagine the massive amount of data that we need to actually record, and how many hard drives or how much storage we need to actually record that. To put the number simple, we were talking here of the order of petabytes of data. Or if you want to talk about Blu-rays, if we want to store the data that we were recording for each day, will be of the order of 800,000 Blu-rays. So that will be, of course, another challenge. That means that for every telescope, then we have to send the data to this supercomputer to correlate the data, to find the fringes. So we cannot send it via internet. It would be too slow. You can imagine sending 800,000 Blu-rays towards the internet. It would take forever. So the most simple case would be just to get all these hard drives, put them on an airplane, and just make the airplane go to the correlator. There will be 2 correlators here, one in Haystack in MIT in the United States, and another one in Bonn in Germany. So we will be shipping all this information to these supercomputers, and there we will be correlating the data, finding the fringes from the signals of these radio waves. More challenge, there will be the correlators that I have been talking about, that will be finding the fringes of the data, or getting together the signals that each telescope pair got, and they will be finding these fringes. So this will be correlating the telescope 1 with the telescope 2, telescope 1 with telescope 3, telescope 1 with 4, 1 and 5, 1 and 6, 1 and 7, 1 and 8, 2 and 3, 2 and 4, etc., etc. So this is also going to be creating a lot more data that we have to analyze later. Another challenge that we will have will be, when do we observe? As I mentioned before, number 1, we have to ask the different facilities if they allow us to observe with them, because of course different telescopes will be busy with their own schedules and their observations. We have to allocate the same time for all of the telescopes, and we have to agree on them. And of course, we need to have good weather, so that we have a clear sky, we don't have clouds, we have a non-turbulent atmosphere, we have little water vapor, so we can have very nice observations. Because normally for radio observations or observations at radio bands, the sky wouldn't affect too much, but when we are going to these high frequencies, this is getting close to optical observations, and then weather will affect a lot. So we have to also be careful with this. We have to find good weather simultaneously at all the stations around the world, which means good weather in Hawaii, good weather in Spain, good weather in the South Pole. So what we are doing is finding a good time in the year where roughly the weather should be okay, which happened to be around April. And we would ask for all these 8 facilities, 8 telescopes, some time around 1 week on April. They would allocate 1 week for us to do observations, and we would hope that during this week, at least 3 or 4 days, there will be reasonable good weather in all the stations. And happily, this happened. So we had 4 days with good weather where we could observe. During those days, roughly speaking, there was no big problems with the data. The recorders were working okay. The telescopes didn't have any engine problem. Everything was kind of working smoothly. So it was, in some sense, a great success. So that means that from many of the years we have had experience, we have been doing observations from about a decade ago, and we have been facing many technical problems, but we have learning from this, and in these observations, things were running quite smooth also. So it was kind of a really great achievement, only being able to get these observations actually properly well done with all the telescopes running and having all the data well collected. So this will be an example of people who were actually observing. On the left side, this would be people in the control room of the SMA, the submillimeter array in Hawaii. You can see on the window the different telescopes that form this kind of small array. On the left side, there will be the control room for the JCMT, with different people who actually travel there to operate the telescope. On the lower left side, this will be people operating the South Pole telescope. And on the right side will be people operating the Pico Veleta in Spain. So you can already see that it's a big effort, including many people. And these people they are not the typical operators for the telescopes. They are really people on this team of 300 people who actually went there to make sure the telescope is working okay. And the mode for interferometry is working fine for their expectations, because as I mentioned, most of these telescopes are generally not used for this kind of observation. So we had to make sure that everything is working fine, that the timer, that the atomic clocks, that the measures are working okay, that everything is on time, that the recording system is actually recording, that all the setup is working okay. We need some operators for this, but we also need special people from the teams to actually be taking care of these kind of situations. Once we observe with the telescopes, you just remember that when we had the telescopes, basically we have, let's say, the slits or the holes in this kind of wall for the double slit experiment. Of course, we will have many telescopes, and it will be not only two slits on a straight line, but it will be a 2D location. So in this panel, what we saw is the position of the telescopes in this 2D configuration. And because that will be seen from the sky, let's say, in this case, we'll be observing M87. So this is a view of how M87 will be seen, these telescopes from Earth. And because Earth is rotating with time, and we were observing for about a day, we would see that the telescopes are moving with the rotation of Earth, and they are creating these kind of tracks as seen from the sky. And from these tracks, this is the regions where we actually be able to get the data from telescopes. And this will be, in some sense, the Fourier transform of what we are going to be seeing from the sky. So there will be two things here. We need a good coverage. We need the more regions of this square are filled out with telescopes, the better it's going to be, because it means that we will have more data in the Fourier transform of the fringes to be able to recover the image. And the second thing that we have to consider here is because the image will be the Fourier transform or will be coming proportional to the Fourier transform of this, the larger this is, then the smaller details we'll be able to observe in the image. And this is also achieved with this kind of configuration with the Event Horizon telescope. So we see that we got very large scales. If we put the scales not in meters, but in the order of the wavelength that we are observing, that will be of the order of giga wavelengths, which is pretty much the maximum we can achieve with our instruments currently. And we have 8 telescopes. Then the feeling that we got in the region is quite nice. So just keep in mind that we are going to get fringes from this space. We are going to get data from this area, this field with colors here. And from there, we had to make the Fourier transform to get the image. So this is how it works. We have the EHT array, which is plotted here. From this, each telescope is going to be getting the data of what the wave looks like for each telescope. Eventually, we will get the hard drives or data modules, which will be collecting of the order of petabytes of data. We will send them by plane to the correlators, and the correlators will find in the fringes, or let's say the pattern that these waves are doing when they interfere with each other. Once we get these fringes, we are going to do the fitting of the fringes, or basically saying calibrating the fringes. And this is going to be producing a correlator that is working basically like 24/7 hours. And then we had to do some analysis and some special programs to analyze this. And then from this fitting, we are going to do the imaging. And for this, there will be different methods and different programs. So what we were doing is We cannot do the Fourier transform directly because there is a lot of gaps, as you saw in the previous image. There are many regions where we don't have information. So we need some special analysis to do this. What we were doing, we were splitting into different teams or sub-working groups, where each working group will be working with one set of program and doing the analysis. Another group will be working with the same program to find the image, finding the image. Another group will be using a different program to do the image. And eventually, every different group would find one image. Then there will be a large meeting or discussion where people would gather together and they would say, I got this image, the other group got this different image, and we will find how robust each image was. How robust in the sense of if there is any bias because of the different groups, if there is any problem because of the different software used, if there is any sort of trouble raising because of the analysis software, etc., etc. So we can actually rely that the final image is free of all these concerns. Different programs give the same result, different people have the same result, different bias are kind of canceled in this sense. So we can really rely on the final image. And this procedure could take of the order of several months to be done. After all this work, you can see how this is going on. We have all this gathering, we have all this group of people who are discussing and finding out what will be the different image, having different traces, ideas. So you can see how the work is done in here. And all this work finally is giving the fruits. So we can actually have a look from one of the telescopes, ALMA. And from ALMA, we can actually point to a particular region of the sky. M87 will be near the Virgo constellation. So what we're going to do here is zoom in that region. And what is going to be shown here is all real astronomical image. All of this is not an artist's impression. This is all obtained with actual observations with different telescopes. So we are zooming in into the galaxy M87. This will be an image by low frequency LOFAR. We can see the galactic jet that I was showing before. We are zooming in into the central regions, or the central region that is causing this. This is the region we could see with the previous telescopes. And finally, with the EHT, this is the image we can see. This image is finally the image of a black hole shadow. So now, this is the image that the Event Horizon Telescope got for the black hole shadow of the black hole in M87 galaxy. You can see here in the center the darkness that is caused by the black hole itself. And this darkness will be, as I was mentioning before, 5 times the distance of its Schwarzschild radius. And around it, you can see all the material, all the crescent disk that is involved in the black hole that is causing all the brightness. This is all in agreement with general relativity. Because if we have the material that is accreting around the black hole, you will have a gravitational Doppler factor, gravitational Doppler boosting. So the material that is rotating around the black hole, and at some point is directed towards our point of view, line of sight, it would look brighter to us because of the relativistic Doppler boosting. When it keeps rotating and it goes, the line of sight is going away from us, then it would look much dimmer. So this is already telling us that this material that is falling into the central black region is actually relativistic to into the black hole. And this is really telling us that what we're seeing here is not another object, it's really a black hole. Just to have an idea of the scales, I took this actually from some XKCD comics. So I have to acknowledge this to the creator of this, but this is also quite accurate. We can see that the size of the black hole, you have the scale there, is about 50 microarc seconds. So it's very clear. You got to zoom before from this real high zooming in that we were getting into very, very tiny regions in the sky of the order of 50 microarc seconds. So basically, if we imagine how would be the solar system inside this black hole, we put the sun where the center of the black hole would be, or the singularity would be. Pluto would be this small circle the orbit of Pluto will be this circle around here. And if we consider where would in this black hole be, the Voyager probe, which is the object that has been traveling farthest away from the Earth ever. This is the object that is farther away from us that we have created. That at this point, people consider that it's reaching the outer regions of the solar system. This would still be within the shadow of this black hole. So it will be still within 5 times the Schwarzschild radius of the black hole. So this picture is giving you the idea of even though the object looks so tiny in the sky, of the order of 1 billion times smaller than the moon, but the actual size of this object is tremendously big, of the order of the solar system. So now something that we can do is we have the image. This is a huge technical and scientific achievement, but of course we don't want the image to just show that we can do it. We want the image to learn things from the black hole. How is this done? We have the theoretical background of the black hole. We have the images with different observations at larger scales. So we have the grounds to create different models. So for different models, we can consider, for example, all this material that is secreted into the black hole, maybe considering a plasma and ions that could be at different temperature, or it could be just plasma, or it could be only ions that are traveling at different relativistic speeds. And they would have maybe different inclination angles with respect to Earth. The black hole may be rotating at different speeds, or maybe rotating in a different direction than the material that is falling. Or there may be all these parameters that we would take into account, or the mass of the black hole will be a different parameter. So with all these parameters and all these models that we have from the theory, we will create millions of templates of the images that we would expect to see. Not only the template itself, but adjusting the template to the resolution that the Event Horizon Telescope has, so that we can actually compare one-to-one the image, comparing apples and apples, not something like a theoretical image with actual image with the constraints of resolution. So we are comparing apples and apples. We have the different models, and we can obtain a set of parameters for the black hole. One of the parameters that, for example, that we got is the mass of the black hole, which happens to be around 610 to the 6 solar mass. 610 to the 9 solar masses. Before, there were 2 ways to calculate the black hole mass, either due to some gas infalling or some movement around, and there was a discrepancy of a factor of 2 between the 2 methods. One method was mentioning the mass would be 3 billion solar masses. Yes? Any question?
No, you go ahead.
Okay, so one method would be considering that this black hole in 87 would have 3 billion solar masses. The other method would consider that it would have 6 billion solar masses, and it would be way beyond the error bars. So there would be a discrepancy of a factor of 2. Finally, because we were able to get this image, we can know that the actual mass of the black hole is 6 billion solar masses. So right now, only with this image, number 1, we already know that one of the methods before was not giving the proper mass. We finally know which is the correct mass of the black hole. Another thing that we can get with the model is we know that the accretion disk, or the material that is infilling the black hole, is rotating clockwise to our direction. We also know that the black hole is tilted to respect to us, and actually the axis of rotation is pointing away from us. So we can get this kind of set of parameters. But we can do even more with this, because we have all these templates, and all these templates were not only considering general relativity. There will be other phenomena that we can also consider. So for example, very simple question, what we see can be something else than that black hole. It could be part of the jet. Like, of course, we know that M87 has this jet that is coming from the surroundings of the black hole. So it could be part of this jet, but it's very unlikely, because the shapes will be not the kind of shapes that we were expecting from the jets, as we saw before. For very similar reasons, it wouldn't be a blob. Plus, if it were a blob, it would be moving at relativistic speeds, which we don't see. We can consider that would be some hollow cone or some hollow structure or some Einstein rings, but we also consider these sort of things in the models. So all these models is already telling us that it's not any of these features. We are not mistaken by something else that is in a similar position with a similar structure, and it's just fooling us, making us think that we are seeing the black hole. It's none of these features. And of course, we also can consider it's not something that is pretty kind of straightforward. Could it be something exotic, something that is even more exotic than a black hole? For example, it could be a naked singularity. This was also taken into account. And then the shadow would be more asymmetric. Some of the models also consider wormholes, and a similar way, the shadow that is observed should be different. So we are also excluding that what we see is a wormhole. And a third thing is we also were considering other theories, non-relativistic theories, and we also saw that we can already rule out some of those theories. Even further, this is probably in relationship with one of the questions I had before, with this interferometric using radio wavelengths of electromagnetic data, we can observe black holes of sizes of 10 to the 6 or 10 to the 9 solar masses. If we use LIGO, for example, we would be observing black hole mergers of the order of 10 or 100 solar masses. So then we can check the properties of black holes at a very, very different scales. Scales of 100 solar masses, scales of millions of solar masses, and because general relativity is scale-free, then the properties of the black holes should be independent in some sense of the mass. So if we combine the LIGO results with Event Horizon Telescope results, again, we will have some idea where we can actually discard some alternative theories that wouldn't be scale invariant as general relativity. So this is also something that we can do. We can already rule out many other theories that are not general relativity. The black hole, all in all, is really proving that what we are seeing there is not a naked singularity, is not a wormhole, it's really a black hole. And what we are seeing here is not some exotic theory, it's in agreement with general relativity. So what we are seeing with this image is really the prediction of the region in the space-time that is broken in the general relativity. We are really able to see the region around the singularity of our theories. We are really looking at the limits of our current general relativity theory, or put it this way, we are looking at the limits of our current knowledge. So it would be really amazing if we can keep further studying these kind of images. There will be more results. I will mention about this later. There will be more images. This is supposed to be the first result of Event Horizon Telescope. There is expected to be many more results. There is expected to be many more things, more ideas, more telescopes, which eventually will be able to reach this. And if we can do that, we are able to be observing the region of the limits of our knowledge. So we'll be able to test for new theories. We will be able to analyze how to understand and how to make new theories and how to expand our knowledge in general relativity, in space and in time. So this is, I would say, a really amazing starting point. So this being said, what is the future? One of the things that the Event Horizon Telescope is doing is during these observations, we were not observing only at M87, the black hole, which will be the second best candidate in different galaxy. We were also observing at Sagittarius A star, which is the supermassive black hole in the center of our own galaxy. This was observed at the same time, but it's taking much longer to analyze because it is in the center, so there will be a lot of other material, other stars, a lot of dust in the middle of the way, so it will be much harder to us to analyze the results. So there will be some scattering effects when we want to observe the black hole in the center of our own galaxy. And of course, all this discussion, all these models are more complicated than for the case of M87, and it will take a bit longer to actually find the reliability for these results. But these results are on the way. And something that is pretty much interesting is that, as I mentioned, the supermassive black hole in M87, the surroundings of it are forming an extragalactic jet, whereas this is not the case for the black hole in the center of our own galaxy. The Milky Way doesn't have a jet. And by observing these black holes, which we consider are the central engines for these jets, we can understand why this is happening, why M87 has a jet, why our galaxy doesn't have a jet, and of course, what are the implications, not only for different objects, but what are the implications for our own galaxy. Our own galaxy, did it have a jet in the past? Will it have in the future? Why it doesn't have it now? If it has a jet in the future, how can it happen? And will it affect somehow the solar system or our own Earth? By studying and analyzing Sagittarius NM87 and in future many more objects, we can try to solve all these questions. That would be one of the key ideas. Then, of course, we want to include more facilities, which means include more telescopes in the network, include higher frequencies, so we can get even better resolution and even more sensitivity, and we can get better details. So we can get much better image, which in turn will mean that we can actually get more sensitive to which kind of theories we can discard, what kind of ideas we can get, and how better we can actually understand and get our knowledge of black holes. Another thing that, of course, is going to be done is to get more and more observations. So with this, we eventually can get time-based observations, maybe dynamics of the black hole, dynamic at events, how it evolves with time, and of course, we'll also have implications on what is the understanding and the knowledge we can obtain for the black holes. So I would say all these sort of things will be very important to actually have breakthroughs in the knowledge that we can get from relativity. Sometimes what I say, a bit joking about these things, is we were able to get a huge leap on how much we understand gravity. I wonder, for example, if these images or what come after this will be the seed to understand gravity to the point in which we can get the technology for, let's say, interstellar traveling. Maybe not in a couple of decades, but I wouldn't be so surprised if we can actually reach this level thanks to the starting point for these observations. So I would like to keep an eye on these kind of ideas. So I will kind of almost finalize there. I want just to say the conclusions for what we have achieved. First, number one, the Event Horizon Telescope is basically a virtual telescope that is formed by assembling a world-sized telescope observing a wavelength of 1.3 millimeters, formed with all these telescopes around the world, and combining them, we can obtain unprecedented angular resolutions. We're not talking about degrees like angular degrees. We're not talking about arc minutes. We are not talking about arc seconds. We are talking about micro arc seconds, which is really a lot of improvement with respect we could do before, orders of magnitude better that we can do with other telescopes. With this amazing resolution, with this amazing sensitivity, with this array, the HT, we were able to obtain the first image of the black hole shadow, and we can see that, number one, black holes are actually real phenomena. They actually exist in the nature. Black holes are not any longer a topic for the science fiction. They actually exist in nature. And not only this, but they are totally in agreement with what we know so far with general relativity. They are in agreement with what we know, but we are going to be able to study further, and we will have a new era after 100 years of the discovery of the Einstein equations, 100 years after Schwarzschild solution for the Einstein equations. Finally, we will be able to study these kind of objects in the universe. So I would say this is the beginning of a great time for astronomy. In Malaysia, for example, in the case, because I'm working in Malaysia now, and there is also Malaysian co-workers, but I would say it's going to be a great time for astronomy in the whole world to be able to study these objects. And this will lead in the future to many amazing discoveries and understanding of our laws of physics and laws of nature. So I think this is everything I wanted to explain. So thank you very much. If you have any further questions now.
Thanks, Carlos. Now the session for discussion.
Hello.
Yes.
So So when you observe the black hole, there is other object near to that black holes. How you will detect the some particular radiation from that black holes?
Mhm.
When you get the radiation from, you get radiation from the stars which are nearby the black holes also. And
Right.
when you correlate all these things from different detectors, then you also get some radiation from other stars near these black holes. So how you will distinguish between these which is radiation from the black hole and from other stars?
hmm Well, obviously, whenever something falls in the black hole, it will fall it forever. So we should expect no radiation at all from the black hole itself. The idea is that if we have stars or ions or plasma or dust or all this material that is infalling around the black hole, this is the radiation that we want to obtain. Because it's infalling the black hole, it will be affected to the gravity, then the velocities will be relativistic. And as you know, if we have relativistic, let's say, electrons or ions, they would emit some sort of synchrotron radiation or this kind of radiation. So this is what we are aiming to observe here with these radio observations. Basically, the synchrotron radiation that is coming from all these objects that are infalling around the black hole itself.
Okay, okay. So we're observing the matters which are infalling to the black holes.
Mm-hmm.
And you have shown that there is on the basis of the models you can get so many images. And
Mm-hmm.
how you choose that which one is the correct one?
Well, of course, what we are doing is not looking at the images, but we will have the model that is creating them and then having an algorithm to do a model fitting. And of course, this model fitting will will be giving us some set of parameters. The most common will be chi-square, for example, or image fidelities, which we can set to figure out which set of models are the ones that fit the parameters better to the actual image that we observe.
Okay, so you are minimizing the chi-square, something like that.
Something similar, yeah. This is kind of saying simple, but that would be the main idea, yes.
And actually you are getting that final image by interfering all the data we are getting from the 8 detectors or telescopes
Mm,
around the world.
right,
So it is the distance between these telescopes also affect the resolution and all these things. And
right.
how you fix all things?
Sorry?
So how you actually, if it is the distance between two telescopes is too much, then it will be the resolution will be less or high.
So, in some sense, what the interferometry is doing is the more separated that the telescopes, then the resolution becomes much better and you can see smaller details. But of course, we're talking about resolution. The other aspect would be sensitivity and how much we can feel this Fourier transformed space. So what we have to consider is if we put two telescopes very far away, yes, we can get this very nice resolution, but we will not be able to get all the details. So
Okay,
what
okay.
we have to do is put the telescopes very far away, but at the same time put other
There's a
telescopes
small.
in between, so we can feel all the Fourier transform regions.
And how you measure the mass of the black holes?
This is pretty much straightforward. When we had the models, you know that the Schwarzschild radius is going to be basically two gravitational constant, the mass of the black hole divided by c squared. So if we got what is the size of the shadow, which we already can interfere by the best fit model, we can get what would be the Schwarzschild radius, so we can obtain the mass from there.
Okay, okay, okay. Thanks.
Hello.
Mhm.
What is the mass of accretion disk around the black hole?
Sorry, what is the sorry?
What is the mass of the accretion disk around the black hole?
The
So
mass.
in this, yeah.
Okay, for the
Mass for the
mass.
accretion,
Hmm?
mass of the accretion disk.
For the mass of the accretion disk, that's hard to answer, both because we don't know exactly what will be the mass, and also because we have to consider about what you consider to be the accretion disk. For example, there will be a region where mass is already infalling around the black hole, but there will be a region that is creating a disk there will be a region that is unfolding as a form of a torus. And so it would depend in some sense about which particular region you're talking about. So in some sense, what we would say, let me remember, I don't have the numbers on top of my mind now, but let's say the mass that is unfolding inside the black hole will be around of a fraction of solar mass per year. But of course, the mass of all the material that is around, all the material that we can see in the image, will be much, much larger than this. But it will be several, I don't know, it will be tens or hundreds of solar masses, but it will be much, much larger than that. But I don't think I can answer exactly what will be the mass of all the accretive material that we see around the black hole.
Okay, thank you.
Hello.
Hmm?
Hello.
Yes?
Yes, so I have one question. The image of the black hole is not symmetrical, right?
Mm-hmm.
The brightness around the black hole. So does it signify the asymmetry of a black hole?
Um, are you talking in the sense of the darkness region inside, not about the brightness outside? Is that correct?
Yes, yes, yes.
Mm-hmm. Yeah, so basically the darkness or the black hole, or how this image is also related with the spin of the black hole. So basically, if you consider the black hole is rotating, then the space-time is also be dragging around the black hole, and there will be a region of the space that will be also co-rotating with the black hole itself. And this is also because in some sense this kind of Doppler effect for the space-time around the black hole, and it's also because in that the dark region that you see around the black hole, what we consider the ergosphere, is going to be changing. That's what I was mentioning at the beginning, that this shadow of the black hole is going to be about 5 times the water radius, but they can change depending on these parameters. The spin of the black hole will be one of the parameters, and this is also one of the effects that they will have. But of course, you also have to consider the resolution effects that we cannot get very much detailed image. So we also have to take this into account.
So what I can grasp from here is that
Sorry?
from this image of what I can grasp from here is that by seeing this image of a black hole, we can't say anything about the isotope. I mean, the whether this black hole is symmetrical or asymmetrical, right?
Mm-hmm. But you
Am I
mean
right?
in the sense, you mean is the black hole is totally spherical or it has some sort
Yeah,
of...
yeah, 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 yeah. That's the same question.
Okay, I don't think at this point we are going to be considering that the black hole is symmetrical if we are discussing about what we consider to be the event horizon, because
Okay.
of course, the event horizon we consider is going to be spherical. The ergosphere, it may be oblate or prolate depending on how the black hole rotates, but these will be assumptions that will be coming from the general relativity. As I mentioned, there will be other theories that are not general relativity that may consider other aspects, and then this kind of shadow will be having different sizes. This was also put in some of the models, and they were also discarded.
Okay. Another question is that in the lower part of the figure, this lower part is more brighter than the upper part. So there is any reason?
Mm-hmm. Yeah, this is the Doppler boosting I was mentioning before. Basically, all this material, this influence of the black hole, is going around it at relativistic speeds. So
Yes.
if you imagine this, there will be at some point in which these particles the speed is pointing towards us, and other regions where the speed is pointing away from us. So of course, in the same way they have get this kind of Doppler factor, another thing that we'll have is Doppler boosting. So the material that is pointing towards us will look much brighter than it is. The material that is pointing away from us will look much dimmer than it actually is. And this is actually one of the proofs that what we are seeing is the material rotating around the black hole. The fact that we can actually see this kind of one side is brighter than the other.
Okay. And third question is that this brightness of the material around the black hole, does it depend on the velocity of its accretion?
Do you mean the brightness as in the image that we get, or the actual brightness in...
No, I mean this brightness has any relation with the velocity of its rotation or accretion towards the black hole?
I don't think the brightness has.
Okay.
If we consider the brightness temperature, I suppose it may have some relation, but I don't have this on top of my mind now. There should be a relation between the brightness temperature of the object, which is how much luminosity it has. So if we can calculate the actual intrinsic luminosity, we can actually observe what would be the speed. So there must be a relation there, but I don't have it on top of my mind at this time. Sorry.
Okay, and in one of your slides, you showed that this galactic center and supermassive black hole, something like this. So, what does it mean by this galactic center exactly?
Basically, we can also observe the center of our own galaxy, and we know that in the center of our own galaxy there is also a supermassive black hole, Sagittarius A star. So what we have done, not us, but the Andrea Gles group has been using the optical VLT telescopes, and then with the VLT, because it's optical, they can actually look at the light of stars, and then they check for different
Yes, this
years.
one. Yes, yes.
That would be the
Next slide.
orbits of those stars. Should be the slide before this one. So you mean this slide, right?
No, next one. I mean,
Which one?
go to next slides.
Uh,
Yeah, go to next slides.
mhm.
Uh, you go. I will tell you.
Okay, I just keep. Have you seen that before? I'm
Yes.
thinking you're talking about the stars
Yes, this
of.
one. Yes, this one.
That one.
The
Okay.
previous one. At one place you mark this galactic center. At the right, you showed the supermassive black holes. So this supermassive black holes and this galactic center both are at different location, right?
Sorry.
This galactic center of the galaxy and the
Mhm.
supermassive black holes,
Mhm.
they are located at different locations.
No, no. This one will be talking about the supermassive black hole that is located in the center of our own galaxy. Just only
Okay.
one.
Okay. Thank you.
Hello, I have a question. How do you choose the locations to set up the facility?
Well, there will be different ideas. As I mentioned, question number one is we need the telescopes to be far away
Okay.
so that we can get nice resolution. Number two will be we also needed to feel the Fourier transform that we want to do with the telescopes. So then, in some sense, we want to have uh, let me go to this exactly. This is oops. Um, like basically what we want to do is put the telescopes in different regions so we can fill with colors this image. So of course, if we put the telescope very far away, we will have the center of the image with a lot of blanks. We don't want to do that. So we want to put the telescopes in different regions to try to fill this here. So not only very far away, but also some of them closer, some of them a bit farther, some of them in between. And what we want to do is also that because we want to observe with all the telescopes at the same time, this means that we have to put them in locations where we can actually observe with the two telescopes at the same time. If we put one telescope, let's say, for example, in a location where we cannot see M87, we can observe with that telescope. If we put a telescope in a position where only one of the two telescopes can see the source at the time, we cannot put the information together. So we also have to select where to put the telescopes considering this. And also very important, we have to take into account the weather conditions. So if we put the telescope in the middle of a city, for example, the conditions are going to be really bad for observation. We had to put the telescopes very far away from civilization in regions that where the atmosphere is very clean, the sky is very dry, the sky is very turbulent. It's not turbulent at all, sorry. And of course, we do studies to figure out what are the best places in the world to put these telescopes. And normally, this is where we put the telescopes. Like, for example, on top of Hawaii, the sky is super clear. So many telescopes are in Hawaii or South Pole. The sky will be super dry. So then it would be very nice to observe the sky from there, or these kind of locations, for example.
Okay. And do you need to take care of the time difference
Mhm.
of the different locations or no?
Right. We need to do because, as I mentioned, we need to observe with all the telescopes at exactly the same time with an accuracy of fractions of a second. So, of course, we need to take into account all the time differences. What we do is we create scripts for the observations of the telescope that take into account all the possible effects, like time difference, even if there is 1 second leap, or if the source is racing at a different time in different regions. We are taking into account all these kind of things when we are doing the observations, and then we are inputting the signal with these atomic clocks to make sure that we are really observing at the same second with all the telescopes.
Oh, thank you.
So, are there
Any,
yes, more questions?
no, I am asking.
Hello, sir. Hello.
Yes.
Yes,
Hello.
go ahead, Swati.
Sir, in LEGO experiment. Hello.
Hello. It's a bit noisy
Yes, sir.
there.
I want to ask a question.
Hmm.
In LEGO experiment, the telescopes make a
Hmm.
triangular shape. So, is there any shape specific locations? I mean, all the telescopes should make a particular shape,
So,
uh, like in LEGO.
okay. So in the case of LIGO, you have to remember that they're still using interferometry techniques, but even the technique is similar. The methodology is very different. What they are doing is checking how the space-time bubbles. So what they are doing is if space-time expands in one direction, the space should contract in the perpendicular direction. That's why for LIGO, they make this kind of triangular shape. For the case of these telescopes, when we set the network, because we are not looking for space-time variations, we are just looking at a radio part of the electromagnetic spectrum. Of course, to fill in this Fourier space, there will be positions that actually are better or ideal to fill within the number of telescopes we have. But in this sense, where we put the telescopes in terms of which will be the locations of Earth that are better in terms of weather conditions, or in terms of observations, or in terms of if we can actually put the telescope there. For example, it would be super hard to put the telescope in the middle of the ocean. We need to put the telescope in the land, and it would be very difficult to put the telescope on top of the Everest, for example. And so we have to consider all these things. We do the best we can. We look regions that are very good for observations, and we can relatively easily access to them. And in some sense, at this stage, this is more of a priority than actually getting the telescopes in the best ideal location to actually fill this coverage.
Okay. Okay. Thank you.
Just maybe for completeness of your question, when we have a network of telescopes that is also using this technique, but the telescopes are very nearby, like we're not talking about thousands of kilometers. We are talking about maybe 10 kilometers, so we can have all of them in the same position. Then yes, we can consider what would be the best layout to put the telescopes in a different particular way. This happens, for example, with the ALMA array, or this happens, for example, with the VLA array. But that's because we can just set a flat land and then put all the telescopes in the same place, roughly speaking, within kilometers. But for this case, because the telescopes are thousands of kilometers away, then we just do the best we can with the locations.
So this experiment is based on uh, double slit interference link. So all the telescope shouldn't be in a line. I mean, you have shown this different locations of the telescope, so they are not in a line.
Mm-hmm.
Uh,
Yeah. Mm-hmm.
so
So
Accord. Yes, yes.
So basically, what we're considering here is the double slit experiment would be a line because we're considering two waves. One is going in one direction, the other
Yes.
is splitting in the other direction. What we are doing here is the 2D version of the experiment. So what we see is not only in a line, but also in the 2D location. But it will be basically the same thing.
Okay, 3D. Uh, 2D. Sorry, I'm
2D.
not getting your point.
Yeah. So
2D
in the
location.
in the
Okay.
experiment, it would be just a line, like all the slits or all the holes in the line would be on one line, so that would be one dimension. But
Mm-hmm.
here we are doing the
Mm-hmm.
two-dimensional version of it
2D.
because we want, of course, to get an image. Not we don't want just one fringe in one direction. We want the fringe that direction and the perpendicular direction, so we can actually see not only how long the image is, but how high the image is. We want the whole image, right? So we had to make the two dimensions.
Yes, yes. Yes.
So are there any questions? I think no. So thanks to Juan Carlos for wonderful talk.
Thank you.
So thanks.